Hello everyone and welcome back to a new video in Robot Structural Analysis Professional. In this video I am going to show an example about the workflow of designing a steel frame, including the connections, steel sections and base plate based on the Eurocode. Now this is a continuation of the previous video in which I talked about the base plate and explained the different types of it. So today I will be talking a little bit about that and the differences between designing a frame with a pinned support versus designing a frame of fixed support, and a little bit about semi-rigid, but without really going into the design process. So with that being said, I hope you enjoy. So sit back, relax, and enjoy the show. Alright, so first things first, I'm going to select something called Frame 2D Design, because today I will be talking about the 2D design only. Now, of course, here I'm assuming that you know everything about the basics of Autodesk Robot. If you don't, then there will be a playlist linked on the top right talking about the basics of Autodesk Robot if you need to brush up on those. Now, this robot has been configured to be using the ACI and American codes for the design. However, I want to use the Eurocode. So the first thing I need to do is I need to modify my codes. To modify my codes, I'll go to something called Tools and then click on the Job Preferences to take a look on the codes that I have. I'm not going to change anything in the units because I'm still using the metric. In the materials, I decided to use the Eurocode, so I must use a conforming database. So one conforming database could be the Eurocode. Just clicking on the Eurocode means that you load in all the data, all the materials that are conforming to the Eurocode. Especially 275 because I'm planning to use it. Then in the databases, there is of course the AISC code for the steel. This is for the database of the steel sections. I'm gonna change that, so I'll expand the database, select steel, and add me a database. This time I'm gonna add me the Euro database, so there we go. I'll click OK. Now in order for this to be always my first choice, I will click on the Euro and then push the up button here, move the selected database up, because usually the first database is the one that is being default active. And that's basically what I want. Now, since the Eurocode for the timber sections and steel sections is active, I still need to check other things. There are no vehicle loads. For the standard loads, I don't think I'm using standard load, so I'll leave it. You could change it. Building soils, I don't care. For the bolts, I care. I'm gonna add me the Euro bolts, so I'll go to the Euro, the ones with the hexagonal bolts. Now, of course, there are multiple ones. Choose the one that is available in your region, because you're gonna construct the steel structure in your region, so make sure that the code you use is including the bolts that you have in your region. For me, this is an example, so I really don't do that. I'll just click and add here. Now, this is not active, so I have to click on it and select the tick button here to make it the current database. For the anchor bolts, you will be using the Polish anchor bolts, and that's it. There are, by the way, no other anchor bolts. The reason why there is only Polish anchor bolts is because Robot has been initially produced by Robobat, which is a Polish company. Then for the design codes, I want to change those things. So first of all, for the steel, I want to use the Eurocode. So EN. Now I'm using the general Eurocode without a national annex. If you want to use a Eurocode with a national annex, then you click on that, click on more, and then select the national annex you want. For example, you could select, now this is an old code, I want the Eurocodes. Let's take a look. So UKEN or PSEN, there we go. This is, for example, the Eurocode of the steel based on the national annex of the UK. Now, I don't want that. I'm going to use a generalistic Eurocode that doesn't include any national annexes. Feel free to choose it if you want or change it. For the steel connections, once again, I'm going to use the general Eurocode. You could click on the three dots here. No, sorry. You could click on the code and select more. By the way, if you click on the three dots, you can see the coefficients of each national annex, but I will not be changing that. You could select more if you want to change the code. However, I'm satisfied by this. Timber structure is not a part of what I want. However, if you want, you could select the Eurocode appropriately to that one. Reinforced concrete, once again, I have a foundation, so I want to select the Eurocode 1992. I don't find it here, so I click on more. Once again, I will go to the generalistic Euro, not a national annex. So I go to the EN1992. If you want a national annex, you could, for example, choose BSEN. This is the Eurocode with the UK annex, but I just want to use the plain old Eurocode. You could select set as current, or you can just click OK and by hand select it as current. For the geotech, you could change it if you want. I mean, you could use the Eurocode 7 for that. Is it the Eurocode 7? I think so. So yeah, okay, set as current, okay. So now everything is Eurocode, but there is one thing missing. You see, if you expand the design codes in the loads, you can see that the load combinations is based on the LRFD. The LRFD is an American standard. So I'll go to more and select Eurocode once again. So select the Eurocode, let's see, equation 610 without the ABs. So where is EN? Let's see, there we go. So I'll add that, select as default, you know the drill, select as default, okay. And it got selected. Those are not part of my structure, so wait, what? Okay, there we go. Those are not part of my structure, so I leave them as is, and that's it. So if you are always working with the Eurocode, then this is a good chance for you to click on Save Current Parameters as Default. If you do that, then every time you open Robot, those settings will be preset for you. However, I usually work with the American code, so I'll keep OK and save the file. Robot detected that some of the member parameters that were used are no longer compatible with the new code, so he's asking me to change those values, convert them, i.e. And yes, they shall be converted, so I click on yes. Now I'll save the file. The file has been saved, and now we can start modeling. So I'll give me a frame that has a 6 meter length, so a bay of 6 meter, and a height of 3 meters, just as a proof of concept. So now the grids are there, and now I'm going to select on members here, and I'm going to make me a beam and a column. First of all, I will select a beam. Now when I select the beam, this is the member type. I might not be happy what the beam is, so I can click on the 3 buttons to change what a beam is, and I want to change it. I want to change it because usually in a steel frame, my following assumption shall be holding true. I'm going to assume that this steel beam is connected to the slab by shear studs, or shear keys, which means that the beam is supported laterally by the concrete slab above it. Now, since it is supported laterally by the concrete slab above it, this will have an implication on the lateral buckling length or the lateral torsional buckling in the AISC code, because you can see here, this is where you can modify settings. I'm not going to modify the pure buckling because this is in the realm of columns, and you can see even that there is an X because we are talking about beams. However, I'm going to modify the lateral buckling because the big thing here is that he takes the lateral buckling length to be the full length for the upper flange and for the full length for the lower flange. However, since I'm saying that the upper flange is laterally braced, now the lower flange, I would assume it is not. You could change it, you could provide lateral bracing for the lower flange, but I will assume it isn't. So now in the upper flange, I will basically tell him that it's continuously supported. How do I do that? I click on that, and now I can change how the critical length is being calculated. Now I could totally ignore this entire thing, but I don't want to ignore it. I want him to calculate. However, when I calculate here, I selected this point. This means like I could select presets or I could select something by hand. So I can input what the critical length is in relation to the original length. Now I could put a 0 here, which means that the critical length is 0, which is the case for continuously supported beams. However, I don't like putting a 0 because I'm afraid that one of the equations might break down, like maybe one of those equations has a division by L. So if I put a 0, then I run the risk of having a mathematical problem. So what I usually like to do is I like to use 0.1 L initial as an approximation of the continuous bracing. I should put a 0. I'm just afraid of an equation exploding on my face, so I'll just leave it as 0.1. Fantastic. For the lower flange, I will assume nothing has been braced. Now, there are a bunch of other things you can check out. Those have meanings in the Eurocode. In the service, if you click on the button, you can see that Robot now deflects or limits the deflection from loads, basically, and I will just leave them as is. You notice that he doesn't add the lateral bracing or lateral displacement check because he doesn't care about that this is a beam. So I leave it for now. I'm not going to change that. Now, if you save it, it will not work because this is default. I need to change the name. So instead of beam, I'll call it my beam. I'll save that and close, and now I have my beam instead of just beam. Okay, so we have my beam. Let's draw my beam. So I select the section. I don't find it. So I click on the 3 dots, and I'm going to go to the Eurocode. Now, if you don't see the Eurocode here, you can click and select it. If you don't see it at all here, then make sure you add it from the job preferences. Now, first of all, I'm going to change the material to something that is Eurocode friendly. I select the S275. Notice, this selection shall not be haphazardly. You should also check with the local vendors if this is available or not. Because yes, you could assume any logical steel strength, but is it available in your region? Because if you assume something high that is not available from the region, then suddenly you run the extra cost of importing that stuff, which might be more than the cost of increasing the section that you're using. So please, before you select the material, check the availability from the local vendors. It's very important. Now I'm going to select the HE sections. You could click on I here to filter them out. I'm going to select the HE sections -B. And to start with, I'll select the HEB 200, which is an I-beam that has a height of 200. I add that and close, and now I'll draw it. So I click on the beginning, one click here, and that shall be my beam. And you can see the beam has been drawn. Now I need to draw my columns, so I select here column. However, I don't like that because the column here might have a different assumption. Let's take a look on what the assumption is of the column. So I click on the three dots here to see what the assumption is behind the column. Now, for the column, you can see that suddenly the bucklings are active and the lateral torsional buckling is not, because usually columns are calculated the strength based on the buckling. Now, before I check out anything about the buckling, if you click on limit deflection, you can see that Robot is even smart enough to detect that this is a column, so I must limit the sideways deflection more than the vertical deflection, because a column usually resists the sideways deflection, which is nice, I guess. Now, in the buckling, you can see that one of the things that you need to check is the buckling length coefficient. Now you have one in Y and one in Z. It's 1, and that's not usually the case, because you know that the buckling length coefficient depends on the end restraint conditions. So if you click on that, you can select any buckling length you want. However, I don't like to select it myself. I'll look at this yellowish thing and click on it, this one. You can see my cursor hovering around it. I'll click on this because this means that Autodesk Robot is going to calculate the K effective length factor based on the support conditions themselves. So he will check the stiffness of the beam with respect to the column and derive a proper K factor for that. So this automates the problem. Now I need to select sway structure because my beam is indeed sway, so I click OK here, and you can see that suddenly you have an auto here. Similarly for the Z, I'll select the automatic and say OK. So this ends everything. If you click on save, it will tell you error because it's the default name. So I click on here and say my column, and I'll save that. I haven't assumed anything about the coefficient of the member length because I'm assuming, and that's important, I'm assuming that the columns are not braced anywhere in the middle. I'll save, and I think I've saved it already. Let me just save it again and close and select it. So now I'll draw me, wait, what? I think I messed up. Let's Control Z. So now I'll draw me two columns. So this is one column and that's another one. Fantastic. We are done. We are done here. So I'll go to my supports and I'm going to select and delete this. This is plot twist. I select pinned and add me two pins. Simply done. Now I need to add the loads. So I click on the load case. I'll add me a dead load and I will add me a live load or a live load, and I'll add me a wind load. Now I need to fill those load cases. So I'll go to the load here and start loading my member. I don't want a nodal force, I want a member force, and I want a distributed force. This is the dead load. Now I'm assuming that the frames are 5 meters apart and that the dead load is 6 kilonewton per meter square. So from the tributary area, you can say 6 by 5 is 30, which means negative 30 in the Z. I'll add this, but before I click here, before I do anything, I check the load case. The load case is wind, which you can see here. However, I just said that this is the dead load. So I have to click here and select dead load, and now I can add it. Fantastic. Now let's switch to the live load and go again. This time I will assume the live load to be 2.5 kilonewton per meter square. And if the tributary area of the beam is 5 meters, this will yield a 12.5 kilonewton per meter. I'll add that, click on the bottom of the beam, and then finally I'll go to the wind. Here, I'll do a rough estimation of 5 kilonewtons. So I'll click on node here, select the load, and ask it for 5 kilonewtons in the X. Of course, you should do a wind analysis and apply the wind from the left and from the right. I'm not going to do this, but I'm just going to show you a proof of concept here. Now, I click on the node here. If I am unable to click on the node, I can basically select it. But I think I am able, so I click here and this adds the load. Fantastic. Now I can start doing my analysis. However, I want, of course, to analyze multiple frames because one of them will be pinned, one of them will be fixed, and one of them will be semi-rigid. So, okay, I'll select this frame, go to edit, move or copy because I want to make 2 copies out of it. So in the number of partitions, I'm going to click on 2. I'll click on the vector and basically like AutoCAD, move it to here, for example. There we go. So now we have 3 copies of my frame. Let's take a look if the loads got copied. So I'll enable the loads and select every single case to check. And it seems, yes, the loads have been incorporated and added. Well, fantastic. Now, the reason why I have 3 frames is because one of them is pinned, which is the case. One of them is going to be fixed, which is going to be added here. And one of them is going to be semi-rigid, just to show you how it's done. Now, I have explained semi-rigid stuff in a previous video. Take a look on that. This is very important. And let me show you the Excel sheet I talked about last time. You can find the link of the Excel sheet in the previous video. Now here in the Excel sheet, this is where the catch-22 problem starts, because you can predict the rigidity or the stiffness of the support basically with given inputs here. And those inputs rely on the section height, the base plate thickness, and the bolt's distance. Now you don't know the section height, and you don't know the base plate thickness, and you don't know the bolts unless you design. And you cannot design without analysis. So what happens here is that I will first of all go to my support and add me a semi-rigid support. Let me show you how the iterative search happens here. So first of all, I click on new support, and this time I want to add a semi-rigid support. So this is going to be an elastic support, because elastic support means that you can apply springs. I'll double click on the label and call it semi-rigid, and I'm going to enable the semi-rigidness in RY, the rotational RY. Any tick you see means that this place is rigid. If you remove a tick, it means you're going to place a spring. Now 0 means it doesn't resist anything, so that is a pin, by the way. Now this is 23,000 kilonewton meter per radian, so I can go here and input the 23,000, but wait a minute. There it was 23,000 kilonewton meter per radian, however I can see a degree here, and you know that there is a difference between degrees and radians. So I need to switch the input units. To change that, I'll go to the Tools, Job Preferences, and in the Units and Formats, I'll expand it, go to Other, and in the Other you can see that there is Angle, Rotation, Data, and Results. Data means input, results means output. Now I want to change the input into the radians, so I select the radians, click OK, and lo and behold, it changed to radian. Now I know it's 23,000 something, but I'll just put 25,000 here to show you the idea. I'll add and close, and now I will apply this semi-rigid to those two supports. You can see the spring icon, which tells that everything is perfect. Now here's the thing. How would I design this frame? This becomes an iterative process. Meaning, I would run the analysis, design the members, design the base plate, and take those design outputs, go here and switch whatever I have here with the design outputs I got here. Switching the inputs would change the spring stiffness, so I would need to go back to Robot, click on the support, double click on semi-rigid and switch it. Of course, if I switch the semi-rigid, everything gets switched that has a semi-rigid. Then since the semi-rigid has changed, this means that the results are no longer accurate, which means I need to run the analysis again, design the sections again, design the base plate again, take the new values to the Excel, and rinse and repeat. Input the new values, get the new stiffness, go back, change, and so on. This becomes an iterative process, but this is how I would design it with semi-rigid. Now this time I don't want to design semi-rigid because I'm going to make sure that my base plate is going to be fixed by adding stiffeners and so on. However, I wanted just to add this for the fun fact and that you can see how the process would look like. Anyway, I will design it, but I'm not going to do the iterative process for that one. So I run the analysis and make sure everything is fine. So let's take a look. Now it tells me separate structure. That's totally fine. I intentionally made separate structures. If I click on the deflection shape, I can see they are somewhat equalish. Let's take a look and amuse ourselves. You can see that because this is a pin, there is a starting rotation in the beginning. And because this dude is affixed, the rotation starts at 0. Because this dude is semi-rigid, you can see that it somewhat has a rotation, but smaller than the pin. This reflects itself into the bending moment diagram, and so on. If you click on Results and Diagrams to Members, enable the MY and hit the OK or Apply button, maybe I should go to Parameters, Labels, Differentiated and Filled, just to show it a little bit, and you can see the differences. You can see some differences in values. For example here, the moment that the support can resist is 36, which releases or relaxes the moment here. It's 64 instead of 68 for the pin. You can see that the support here carries moments. The support here carries less moment because it is less rigid, and the support here doesn't carry any moment because it doesn't resist any rotation. Because I usually teach my students that, hey, if you want to resist movement, you need a force. And if you want to resist rotation, you need a moment. Vice versa, if you want to cause a movement, then you need force. If you want to cause a rotation, then you need moment. So because it stops the rotation entirely, you need a large moment. because this stops the rotation partially, you need a smaller moment, and because this doesn't stop the rotation, you don't have a moment. Fantastic. Now the analysis is complete. I cannot simply go to the design because I need to make me some combinations. Now I could manually make my combinations, but I'm kind of lazy. So I'll go to something called loads and automatic combinations, meaning that I will let the code run the combinations. Something very important to notice is when you click on automatic combinations, double check the combinations according to which code. You can see the Eurocode here. The reason behind this is because once again, in the tools job preferences, I remembered to expand the design codes on the loads and set it to load combinations Eurocode. Otherwise, you will have different combinations. So I'll go to loads, automatic combinations. I'm gonna make me, I don't know, simplified or full. Let's just keep it full, I don't know. So it makes the combinations. You can, wait, what? Again, loads, automatic combinations. Okay, it doesn't do anything. Okay, maybe I should run the analysis. That's new. It usually does it automatically. Let's take a look. Oh yeah, there we go. You needed to run the analysis. You can see a lot of combinations, THIA and SLS and ULS and so on. Let me show you something. If you click on ULS, this is the ultimate limit state, which is also called the EQU state. This includes a lot of combinations. If you click on this, the select component, you can see the combinations. I think there are like, I don't know, let's take a look. There are 10 combinations inside the ULS. For example, if you stand in the first one, you can see 1 times 1.35, 2 times 1.5, and 3 times 0.9. What does this mean? This means case 1 is multiplied by 1.35, so dead load multiplied by 1.35, plus case 2, which is the live load multiplied by 1.5, plus case 3, which is the wind load multiplied by 0.9, and so on. You can check out different cases if you want for the ULS and SLS. Notice, to access this, don't select the envelope. No, select without the plus and minus. You could select the SLS here and see the different combinations that you can see here, like dead, live, and some wind. So yeah, I think that is fantastic. It has been done automatically because I want him to design using case 4, ULS. So how do I start my design? Well, to start your design, you select on design and you go to steel member design. Notice the aim of my video here is to provide you one full lecture explaining to you the workflow of designing a frame. I know that this is a simplified frame and there are no problems in stability, but I think I have like over 150 videos, so I'm pretty sure if there's something missing in that and that you want to learn it, just search on my channel and you will find definitely a video about that. Alright, so let's start designing. Now you cannot design without groups. You need to group those things together because for now, if you click on groups, there are no groups. The only thing you can do is something called member verification, which means it checks the member if it's adequate or not. Now, I don't want to check the member, I want to design it. So I need groups. Of course, here I'm gonna group the columns together and the beams together for each individual frame because the frames have different behaviors. So okay, I will now select what I'm gonna select. I will now go to the groups here and basically click on new to add me a new group. So it has group number 1. The member list is gonna be those two dudes selected. And the name is gonna be, what can I call it? I have no idea. Maybe frame pin. Okay, frame pinned columns. This makes sense. Now for the sections, I need to tell him what sections he should try when he wants to design. So I can basically click on Europe here. There are a lot of section families. I can filter them to the eye and select HEB. So you can see the selected sections are here. I click OK and save. This saves. Did I click save? Yeah. This saves the group. Now here I will go to new. This is group 2. This time it is going to be the beam. And I want to rename it to become frame pinned beam. And for the sections, I check, yep, indeed, those are the sections I want. Wait, I thought I selected 275. Why is it 235 here? Okay, let me save first. Let me check something. I have a bad feeling about this. Let me see what I did here. So what is this? Let's click on that. Let's just check the material. Where is the material? Let's click and search for the material. It is 275. Okay, let's select here. Is this all 275? Yeah, it's 275. I didn't mess up. Into the design by clicking design, steel member design. Okay, now we are here. I think that's surprising. I thought that Robot should be smarter than this. I thought Robot is going to select the material automatically based on the definition. It didn't. So should I select the material by hand? Where is the material? Oh, there we go. S275. I don't think I should do this. I think it should be automatic. Okay, my error sensors here are tingling, but I will select S275 and hope for the best here. Because I have already defined S275, I'm surprised why I need to select it again. Anyway, it seems to be strange. So let's go to the steel S something. So S275. I am kind of spooked now. Okay, back to here. We select new now and define us a new group. This time I will select my columns here and the fixed frame. So now this is frame rigid or fixed, and it's the columns. I'm giving some names for those so that it makes sense. In the sections I check, yep, the HEB are selected, and that's it. I will save and make me a new one. This time I'll go to member list, delete this, and select the beam. Now here I will call this frame rigid beam and double check the section. Section is okay, so I'll save and click on new. Now this time I will select the columns of the semi-rigid, despite the fact I will not be giving it too much attention, but just to show you one iteration here. Not fully, just to show you. Semi-rigid, and yeah, I think that's correct. Sections, yep. Save and new. I called it beam. Okay, let's go back to 5 and call this columns and save, and then go to 6. Okay, that's a beam now. And we delete this and add this. I think I should check what I have done. In the sections, check, everything is fine, save. Okay, let's double check very quickly. So let me open the member numbers. So in group number 1, that's 3, 4, that's true. Group number 2 is the beam, true, 9, 10, 8, 6, 7, and 5. Okay, I think everything checks out. Fantastic. Now we have defined our groups. It's time to duel. No, wrong show. So I'm going to design things. I'm not going to do verification. So I click on code group design. And I'm going to design all the groups. So I can simply write ALL for all, or I can click on the list and select all here, which will add 1 to 6, which means all the groups from 1 to 6. Now there are options you could choose, and there are configurations you could change. I will leave this for you because I think that you are Eurocode professionals. In the ULS, I want him to design those things based on the ULS combination, which means now that the combination of the ULS is combination 4. So I'll tell him design for combination number 4. And that's it. Let's run the calculation, hope that something is working. So it seems things are working. Okay, how do I read those results? Now you can see that each group gets a group designation, and it gives you the member that controlled the design, the best section of the controlling group, and the controlling case, ULS-1. -1 because the ULS had multiple components. Let me remind you, if you go to ULS and click on this, you can see multiple components of the ULS, and -1 means that it's the first component, so this has controlled. Okay, so everything seems to have been designed. Now, I am not happy about this design. Although everything is green, I am not happy. Allow me to explain to you. What I'm saying here is that take a look at frame pinned column and frame pinned beam. So you're talking about those dudes. The frame pinned column's best design was, oh wow, surprisingly, HEB 200. So the section I chose was the best section. However, for the beam, the best section was not HEB 200. In fact, it fails. You can see it's in red. But the HEB 220 is the best section. Now here I have a problem. Not really a problem, but I have a practical issue. The practical issue I have is that if I can, and if it is economically viable, I like to have my column and beam having the same section. However, as I see it here, I can see that the column wants to be HEB 200 and the beam wants to be HEB 220. So I'm kind of annoyed. I think it is worth it if I make them all HEB 220 because, practically speaking, on the construction side, having the same beam height might decrease the complexities of the connection. I don't know. You might disagree with me on that one, so feel free to choose whatever you want here. I am going to stick by my decision here and use the same section for both. Now, if you click on Change All, this doesn't do what you want. Because if you click on the section, you cannot see it, right? Okay, let's see. Right-click here, Display. How can I show the section? Let's see. Member description, section names. There we go. There it is. Member description, section name, apply, just to have an idea what is happening here. So look what happens if you click on Change All, or Change Now, Captain Guinea. I'll change all here and I'll add and say OK. And you can see now that the beam has got to the 220, sorry, and the column got the 200. Well, that's not what I wanted. Do they have the same width? Let me check something. Because if they have the same width, I can let it slide. Let me check something very quickly. I'm sorry about that. Let's see. So it is the HEB family, so HEB, and it's 220 and 200. So the 200 has a width of 0.1 or 0.2, how fitting, and the 220 has a width of, it's ugly. It doesn't work. It works, but look, this is what I mean. I'm thinking loud now. I'm thinking practically. Practically speaking, you can see that the beam is slightly larger than the column. Now you could have a connection. I don't know. You can let it slide. It's just 10 millimeters. I want to stick to my guts and say that, hey, I want them to be the same section because it is still economical, by the way. It's not a huge increase of a section. So, okay, how can I do that? Well, wait, can I simply select this and click change? Does it work? Let's see. So if I select the column and ask it to change to this one or here, okay, which one is it? I select this one now. Oh, it changes. Oh, this is even easier than I thought. Okay, I changed that. I will also change this. So I go to the group, which is this dude, and change basically. Okay. And this one is already working. Fantastic. Now, what happens if the section that I want here is not there? Well, if it is not there, then all I have to do is to go to the group, like, for example, frame rigid columns. Frame rigid columns, where are we? Which is this now, I think. I think that's one. No, there we go. Frame rigid columns. And in the sections, I can delete and force him to take a certain section. And then I'm guaranteed to have it. Like I could delete everything and force him to take 220 only. Only 220. Let me show you. I delete everything, select Europe, select the I section HEB, delete everything again, because I don't want everything, and basically go to the 220 and double click on that and add it. How does it get added? Can I even add that? No, don't tell me I need to delete everything. Let's see. If I select, oh my God, I need to do this by hand. Like I need to do this and delete. By the way, Control Shift is what makes it select everything like this. Okay, I can do it like this, I guess. Like force him to take 220 and then he has no option but to take 220. If it is adequate, of course. But I think I was lucky to have them close to each other. Anyway, I changed them. Now, since I changed the sections, the stiffnesses have changed. So I need to... Okay, why is this not changed? Did I miss something? I think I missed something. Let's do it again. Yeah, it's warning you for something I'm going to warn you anyway about, so give me a sec here. Rigid, where is it? Semi-rigid? Semi-rigid columns. Yes, change it to this one. Okay, now it's changed. You see there is a problem now. Since I changed the sections, it means that the stiffness has changed. And if the stiffness has changed, this also means that the analysis has changed. So I need to run the analysis again, which would change the distribution of moments because the stiffnesses have changed. And now once the analysis has been run, I'm not going to make a design, I'm going to make a verification to check if the sections still hold with the new analysis. So I'll click on calculations to see if everything is fine, and indeed everything checks out. Everything is in the green, the columns are in the green, the beams are in the green, everything is perfect. And by the way, it's pretty interesting how the calculation sheet looks. It even tells you exactly how and where it gets the values from. You can even go to detailed results to see everything yourself and how the values have been taken, what equations were used. This is eye-opening for a student if he's still learning this stuff. Okay, so we changed our sections and we checked everything checks out. Now, we're not finished yet. I could save everything. Like, look, if I want to make money out of this, like if this is a project I wanted to make money out, I will click on that and basically select calculation note here. It opens for me a calculation note for this group and save it. And then I would click on the next group, like group 2 or group this one, click calculation note because I need to prepare a calculation file. You know what? You want a full file for that? Let's do this. I'm going to click calculation note here, file save or save as. And I'm going to make me a full folder here. On this folder, I will say calculation results. Now this is going to be frame pinned columns. You want a professional output? You get it. That's the first one. For the second one, same thing. Calculation note, file, save as, and again, frame pinned beams. And the next one, and rinse and repeat. Now I'll keep it this for this frame only because I don't think I have a project where I have to compare all 3 frames. So I'll keep it limited for those 2 frames. So I have exported the calculation node of the pinned frame, but that's only for the steel structure. Now, I finished the design here. Of course, in the semi-rigid, I'm not done because suddenly those things change, but I will not change anything here. What else do I need for the design here? I need to go to File and go to something called Printout Composition, because I also need to export the results of the analysis. Now, there are templates for this. I could export the data. So this is the data inputs, and I want to export the results, add, and this is the analysis results. I can print them. I could also add the steel element design here, but I already exported it, so I'm not going to do that. Okay, it's asking me to print, so I'll print it. Okay. And now finally, I need to design the connections. I'm going... Wait, what? Again, recorder guy finds ways of breaking robot. Fantastic. Now, okay, we continue, even if it's broken. So I have designed the members. Now I need to design the connections. Now, how do you design the connection? You click on Design and you select Steel Connection Design, which opens a new GUI. Now, how do you design a connection? Well, it's actually easier than you think. I will remove the sections first, and don't make the beginner's mistake. If you select the node, you think that you can design a connection, but if you click on this, it tells you, I'm sorry, I cannot do anything. You see, you have to click the node and click the nearby members for it to understand what you want to design. So now I selected those things. I click on Connection Design, and now it understands that it's a connection, it's a frame knee, and it opens the design stuff for me. Now here the good news are, it takes the loads automatically from the analysis and asks you some questions. All those distances, all those values need to be inputted by me if I don't import. However, since I imported the frame connection from the structure, it took those values from the structure itself, everything from the sections, which is fantastic. Now here, because it's a rigid frame knee, I like usually to apply stiffeners and whatnot. Now I am going to do a blind analysis without adding anything. So I click apply. Now I'm just going to do a blind analysis here. Once again, I see S235. That's odd. Oh yeah, okay, fine. If I remove it, this is not S235. It will automatically use the same material for all components. So I think it should take 275 here. I'll click apply and OK here just to see something. So this is a blind thing, right? And I will run the calculation here. This is a design of steel sections. I just want to check if it works or not. So connection verification for the load case is 4. I don't need all of them. Wait, list combinations. Code combinations. Ah, nice. If I click on code combinations, it selects the code combinations directly, which is nice. I don't think it will work. Yeah, it doesn't. Of course it doesn't work because it's not that strong. I didn't expect it to work, by the way. And now I am worried. I am worried because listen to this very important thing. There might be a chance that I need to increase the height of the sections, not because the sections are weak, but because the connection needs a higher section to assume rigidity. So, okay, it didn't work. That is because I haven't added anything. So let's start adding some stiffeners, like brackets here. It's a rigid support, so of course there should be a bracket. And let's add stiffeners, because it's a rigid support. There should be stiffeners. And vertical stiffener, do I need it? Let's add it. You know, it's just a software. I can add anything. The cool thing about the software is it does everything for me. I click OK and apply, and run the calculation again, hoping for the best. Okay, I just click load calculation. Let's see what happens. And it doesn't work. Fantastic. It does not work. Oh, this is bad. Okay, so there is a problem. The ratio is not enough. Let's see why. So where is the problem? Let's go down. Where is the red lines? Ah, there we go. Not verified. Why? Because MB1, there are a lot of other checks that check out. Everything checks out, it seems. The problem is with the moment resistance, I guess. So we need to change some stuff in the connection. Now I'm running out of options here to strengthen it, to be honest, because I don't want to increase the size of the section for that matter. Let's check out how I can do that. Fine. So what am I missing here? Can I strengthen it with a plate? What about the bolts? How many bolts do I have? I have M16B, unthreaded portion. The number of rows is 3. Wait, I can increase the number of rows to 5. Maybe I can add me some bolts. Okay, apply. And run the calculation again. So I added the rows of the bolts. Ah, see, it has a positive effect. But I think I'm overbolting the thing. I can only go like 2 more and that's it. So let's try it again. I could also change the class or the... Wait, I have to give it the diameter? For real? So I can just change the diameter? I thought it should be done automatically. Okay, apply and run. No, it doesn't matter. It doesn't change anything. It just made it ugly, but no, it doesn't change anything. And I am literally running out of options here. Let's take a look. So let's go back to 16 because that didn't help. I will just change it to 7 one final time. And that's the best I can do. More than this, I cannot do. Let's calculate again. No, it didn't change anything. Wait, now, first of all, it looks ugly. It's impossible to do here. Also, the ratio didn't change. So what gives? It's going to be a 3-hour video, right? Okay, so what's the problem now? It's the MB1ED. Oh, fine, so 5 is actually something that I can stand behind. You know what? Let's just try do stuff. Maybe I should do welded. Maybe I should go for the welded beam. Okay. Are you going to work? Come on. Oh, it was... Oh, really? That's it? It's because the bolt didn't work? Okay, if you say so. Okay, he's doing the welded here. I did a welded connection. Let's see. But I should check that out in the result. Can I see the welds here somewhere? So. Weld. Yeah, okay. Yeah, it does the welding. Okay, fine. And it checks everything. Oh, look. SJ initial. Oh, wow. This is cool for the semi-rigid thing. Of course, here it checks if the SJ initial, which calculates from here, it's infinity. Okay, how do you get infinity here? Based on some equation, right? Something is 0 there, I guess. Okay, so fine. I'll take it, basically. Everything seems to be fine. So I think I don't need all those stiffeners, do I? Let me just check, because I don't want to be wasteful. The bracket I will keep. I usually like to have brackets, but the stiffeners, maybe I don't need them. Let me change this. Nothing here. There we go. Okay, I'll apply. Let's calculate again. Okay, it says of course, it says it's not strong enough. So, okay, I'll just add the brackets then. Fine. At least the column brackets are important. So let's add them back. And you know what? Let's add the stiffener to the beam. Okay. Beam, I forgot to do this. Beam real length is 6 meters. That's true. But the frame is not braced. It's sideways. So apply and okay. Oh my, let's hope it works again. Yeah, it works again. I was afraid for nothing. Now I want to export this. How do I export that? Control P. So if I click here anything and say Control P and then print. Nice. I just have to click Control P. Just push Control P and you can print. I'll take that. I'll take the W. Okay, so this is the frame knee. I go back to, I'll just go to structure view. Okay. Now I finished the frame knee. And that is that. Let's go back to our structure, or let's just go to the structure. We finished the frame knee. Of course, the same will apply to all the frame knees, but I don't care about them now. I care about this. And now I'll go again to design, steel connection design. Now I finished this connection, so I go to structure. Now I want to design the base plate, and I want to design it for this and for this. So I click on this and go to this button, which is the new connection from select members. It will not work, because I selected the pin, but I didn't select the member. Here, look, if you click on that, it tells you it doesn't work. You need to select the support and the element, and then it will work. So now it sees, and look at Robot's smartness here. It says pinned column base, because it knows you have assumed a pin, so it makes you a pinned column base. Now, I will accept everything blindly here. I think I should go here. Yeah, it's sway. Fantastic. Now, I will accept everything blindly because I want to show you something very cool. So I'll go OK here. So it's accepted now. Here, I will click on that, and I will click on the new connection. And you can see it says fixed column base. And I'll click OK. So now, because you added a fixed support here, Robot will tell you fixed column base, and here pinned column base. And look at this cute little figure. One of them has the bolts in the middle. One of them has the bolts on the outside with a stiffener. Now, I will just run the calculation for everything. Okay? Just a blind run for this and for this, for everything. Now, of course, the fix doesn't work, and I will show you why. So I click on here and show you the view. Look how Robot deals with a pin support. It adds the bolts in the center because it doesn't want to have any mount resistance. If you go to fixed, it adds the bolts on the edges. However, I said before, that I don't like that. I don't like the bolts only. You need to add some stiffeners. And by the way, you can see that robot tells you there is an error in this connection. Now, if you click on that connection, you're going to go to results and see everything checks out. This one doesn't work. Of course it doesn't work because I just did some garbage connection. I said before that I want it to be rigid. So I'll add me some stiffeners. And you know what? I'll add me at the highest stiffening possible. Oh, this is Novacan. Let me just add simple stiffening and see what happens. So those stiffeners are there now. I'll apply and run the calculation again. So let's see what happens. Okay, it's getting better, but not good enough. Wait, am I doing it right? I want code combinations. I think I messed it up. Let's try again. Okay, it's still the same thing. It doesn't matter. Continue. What about this? This is the base plate. The material should be 275. Why are you forcing me into this? Let's see. This is 275. That's 275. Stiffeners. What is this? I can choose. I'll leave it for now. Anchorage because of pullout. Oh, there is a lot of things to do. This wedge is for the shear so that it doesn't get sheared off. Welds. I don't want to weld anything. For the foundation, this is the design of the foundation of concrete. Let's calculate and see exactly what the problem is. Let's see. Let's close this and take a look what the problem is. Okay, not verified. Okay, the moment capacity of what? Connection capacity check. This is the connection resistance to bending. Okay, the bending is not enough. That's the reason. Okay, so since the bending is not enough, let's improve it. Let's go to the connection and let's check out how we can improve the bending. I can improve the bending by changing the bolts and increasing them. Added, let me see. It added, how many bolts did it add? It added 4 anchor bolts, right? And those are the things here. Okay, here. Number of rows, number of columns. Fine, let's increase them. Let's give us here a 4x4. See what happens now. And apply. I increase the number of anchorage bolts. So let's take a look at the analysis. Oh, wait, it's outside? How is it outside? Who told you this? Let's go back to 2x2. Let's calculate it again. Yeah, sorry, run. Wait, this is German, Durchmesser. What is happening here? Now, first of all, the plate. The plate size I can control. And if I control the plate size and the plate thickness, then I can control the number of bolts I can add here, right? Right. Okay, so the plan would be 440, 440 makes sense. So, and I'll go back to the anchorage here. 440. Wait, what is he doing here? What are you doing here? There we go. He's saying that those are 330 and those are 110. Okay, now I know. If I want to add more bolts, I need to decrease the stiffness here. Let's put 110 here and add a 4x4 just to have some bolts. If I click equal spacing, will it understand? But if I put 5 here, will it change? No, nothing. What a shame. Okay. Calculate. Calculations. Yeah, okay, at least I was able to understand how this one worked. Doesn't look nice. Connection capacity check. So it's the moment, right? Okay, it's the moment. So what's the problem? It says that connection resistance for bending is this one, based on some equations. Does it do a foundation check? Yeah, it talks about the concrete. Okay, it does do the foundation check. How can I improve it? Okay, let me think loud here. So usually moment means force by distance. Now, if the moment is large, then I can increase the distance or increase the force, right? Right, so let's increase the force first. So I'll double click here. Now the things that create forces are, I need to go back to the basics here, are the bolts, right? So I could decrease the number of bolts and I could increase the diameter of the bolts. Let me just go with 30. No, yeah, 27. Okay, fine. And okay, and calculate. So now I've chosen larger bolts. This should be not safe. Of course, because I changed. Oh my god. I want them to be on the 4 edges. So let's add us bolts on the 4 edges, meaning I should have 330 here and 330 here. I click apply and OK and run the calculation again. Okay, 3.51. Fantastic. Nothing has changed. In the scheme, I can see them on the edges. That's exactly what I want. And the connection view, I can see them there. They are larger now. Are they larger? In the scheme, I can see those are D27. Nothing changed by that. Connection resistance for bending. There is the lever arm for the compression, lever arm for the tension. I think the connection is too small. Let's take a look. 800 by 800 by 900. That's what I said. Fixed connection is going to be a pain, and you can see what I'm saying here. Because you have to resist the rotation somehow. And you can see the outcome or the outlook of my previous video in action here. I'm really struggling to design the foundation with a base plate. Okay, let's increase and calculate again. Do not change anything, of course not. Oh, it changed, okay. But now I have, okay, what I've done just now, this is gonna be hard. I've increased the base plate size, which means I need to increase the connection size. So let me increase the connections, the foundation size. Let's put it to 1 meter. Okay, apply. Now I increase the plate, which means I have some space for my bolts. So I can go to my bolts now, and I can space them further apart. So instead of this, I increase the base plate to 400 from 220. I added 200 here. So I can add 200 here, or 160 here. Let's say 450 here, and 450 here. And let's apply and run again. I'm increasing the base plate, so it should increase the stiffness. Yeah, see, we are approaching. Okay, fine. There is some hope now. There is some hope. Okay, so there is some hope because the stiffness of the plate got increased. What happens if I increase the number of bolts? Will this help? Let's increase the base plate a little bit. I'm not really happy about increasing the base plate. This will bend the base plate because if I increase the base plate a little bit, let's go to 700, and that's the last thing I will increase here. This is the last thing I will do. I will not increase it anything more than this. I will give up after that. Okay, so it's 700, 700, right? Right. Now I can increase those, and I increase the thickness of the plate because it must resist the torture of bending. This is going to be a spicy thing. So 700, I increased by 100, so I can increase this by 100. So in the anchorage, I can go here all the way up to 600, I guess. This is the max I can go, 600. This is like Kaioken times 20 here. So now if you're asked, this is too much on the edge. If you are still listening, I commend you. Like, thank you very much for doing that. You are witnessing my torture. Let's run the analysis one final time. And come on, man. Just, so close. So close. So bloody close. The problem is in the moment, right? Let's take a look. Yeah, it's still in the moment. Wait, maybe I can do this. I don't think it will work. Apply, okay. Like change the anchorage of the bolt. It would increase the tension. Okay, it would increase the tension. Fine, fantastic. Oh my god. I think I know now why the reason was. The reason why it was unaffected is because it seems that the load of the pullout was high, and that was why there was a limit for the total tension on the bolt, and that's why it was always failing. Now I got it. Yay, I finally finished it. So I can go to structure and feel free and feel happy about myself. I think mission accomplished. Let me recap very quickly. What I have done is I have shown you a full process of analyzing a frame, with all the shenanigans that comes with choosing the sections, aspects of choosing a section, connection design, foundation design, and so on. See the reports for I think this is the beams, and the columns, and the connections in PDF. This is the analysis. This is the analysis report. That's design of the pinned base, column base. That's design of the fixed column base. And that's the design of the frame knee. Of course, here you might be wondering, in the calculation report, why is it so bland? Title page and project and author. You can customize those things by going to Robot, going to File, and there's something called Project Properties. And here you can add a lot of things. Everything you add here will be shown on the title screen of this report. So I think you've done a good job, and this is the workflow that I would be following if I have to design a steel structure. Here I did a simplified frame, but of course you can extrapolate this onto a structure. So yeah, that's everything I wanted to talk about today. I hope you enjoyed, and in the end I want to give a full workflow sized shout out to my dear channel members in the contributor level and the helper level, whose names are going to be shown on the screen. I want to thank them from the bottom of my heart, as their support to the channel is priceless to me and enables me to provide you with videos hopefully on time and with a certain quality I try to achieve, and for that I am forever thankful. In the end, I hope that you enjoyed the video and you found it beneficial. If you have enjoyed the video, then please consider liking, sharing, subscribing, commenting, and so on, especially subscribing because it helps increase the reach of my channel. As per usual, this is the Civil Engineering Essentials channel, and we'll catch you in the next video. Bye bye.